So we've got that formula. I wanted to pause it there for a second and make sure my recording's going through okay. So we need to find the area of these four shapes that are on the middle of your paper. Of course, some of these are review. We did throw a triangle on there, a couple triangles on there. Then these two are the new ones. One looks like it might be a rhombus. One looks like it might be a kite. So let me give you some side lengths and kind of let you have a few minutes to go for it. Of course, now that I see it's cut off on your screen, this top number is 5. So all these sides are 5, which tells you, of course, what kind of shape that is. You may want to pause it and try to work. If you want a little more information, I will tell you some information about the diagonals of this shape. If these are all 5, of course, you remember it's a rhombus. You remember the rhombus's diagonals bisect each other. So if this is 4, this is also 4. You know they're perpendicular, so you could actually use Pythagorean theorem to find this length right here. And I added some information over here. I probably shouldn't have. At this point, you should be able to find the area of both of these pretty easily. You didn't need this. If you remember, this is 8, this is 8, this is 8, because it's an equilateral triangle, which means all the angles are equal, which means all the angles are 60. So, again, you can pause it and go for it, or you can follow along with me. I'd prefer if you'd kind of work on your own and check. Hopefully you've drawn an altitude on that shape. Originally this whole thing was 8. It's going to cut these two pieces, so they're both 4 now. And you actually have plenty of information on there to find the area of that triangle. This entire thing is 8. Each one of these are 4. If you either use your 30, 60, 90 ratios or use a sine ratio, you could find that this altitude is approximately 6.93, which I believe is 4 rad 3. You could use your 30, 60, 90 ratios as 1 to rad 3 to 2 for just this little triangle here on the side. But I believe you should come up with some sort of area around 27.7 units. So check that if you haven't gotten that correctly. But again, this is the base. This is the height that I got using either sine or 30, 60, 90 ratios. On the second one here with the rhombus, hopefully you see a Pythagorean triple. This is a 3, 4, 5 triangle. This is a 3, 4, 5 triangle. They're all 3, 4, 5 triangles. So you could very quickly do the new formula, diagonal 1 times diagonal 2, and don't forget to cut it in half. So diagonal 1 could be the 6, diagonal 2 could be the 4, and quickly do a 6 times 4, you get 48. If you think 48 is the answer, as you probably did with the triangle, you forgot to divide by 2. So it should be 24 square units. If you remember this problem actually came up during Mrs. Christiana's teaching. I think she assigned this problem for a homework one night. And wasn't sure why the area wasn't 25. If you imagine this as a square, if I were to make these all right angles and stand it up, the area would be 25, which is a little bit more. It would be base times height, 5 times 5. If you imagine this thing slanting over, that area is going to get smaller and smaller and smaller the more I tilt that down to bring the bases basically together. So, should have been 24. Go ahead and try these two. You got a kite right here. You can tell by the diagonal being bisected. 5 and 5 are the two pieces there. The longer piece down here, 11 and 4. They are perpendicular. I threw a right angle box on there. This is a right triangle with a 32-degree angle. Again, you may want to pause and work on your own. If you're not, hopefully you realize you don't have the base. I would call this the base, and I would call this the height. It's just flipped upside down. That's the base, that's the height. If I give you the hypotenuse, hopefully you're thinking sine and cosine to find those two values. So hopefully somewhere on your paper you show using sine and cosine of 32 to set up an equation and solve for those two sides. I think those two values look correct. Multiply those, you get somewhere around 45. If you forget to divide it by 2, you'll keep it as 45. You remember to divide by 2, it should be around 22.5. And of course the bottom one, you have no base, you have no height, but you do have the dimensions for each of these triangles. So you could find the area of this triangle, plus this one, plus this one, plus this one. Or you could just do what we did up here. Diagonal 1 times diagonal 2 is that new formula for kites and rhombuses. So you would do 10 times 15, and then cut that in half. Should be 75 square units that fit inside that kite. Hopefully that seems pretty straightforward. So these are just two new formulas that make things a little more efficient. There's certainly other ways to do this by breaking things into triangles. So give you a second to try the two sort of word problems on the bottom of that page. They're not tricky, but they force you to draw your own sketch and to interpret the words as you read them. So sketch a parallelogram with a 45-degree angle and sides 4 and 6, side lengths 4 and 6. You can pause and work through those and then check if you want. So there's a parallelogram. I just threw 4 and 6 somewhere on there. And you go, I got a 45-degree angle. 45 wouldn't make sense over here because it's obtuse, so I'd throw it over here on the acute side. Hopefully you think, oh yeah. Or remember on Friday we were drawing altitudes quite a bit. You can throw the 45 up here or down here, either one. And maybe do some trig on here. Area of a parallelogram, maybe you have to look back at your other paper, of course, is base times height. So here's my base. I'm calling 4 my base. This would be my height. So I'm going to use this little triangle here to find my height of my parallelogram. So you kind of ignore this part for a moment. Hopefully you can sine ratio again. The opposite side, the hypotenuse, the height here over the hypotenuse. And I believe the height of this thing in this situation becomes 4.24. And you're ready to go. Base is 4, height is 4.24. Multiply those, you should get around like 16 or 17. Now some of you may look at that and go, wait a minute, that makes no sense whatsoever. That doesn't make any sense at all. The answer for this sounds like it's 17 square units or squares. Hopefully you look at this and realize this makes no sense. If this is a 45, 45, 90 triangle, and this is 4.24, this would have to be 4.24. Think about that. Why can this not be 4.24? And you might realize this whole thing is 4. This is a dilemma you get into when you're sketching your own drawing. As it turns out, it doesn't matter how you sketch this thing. And of course, I don't know why I'm jumping down to that problem. It doesn't matter how you sketch this thing. You could have switched these two around and put the 6 down here and put the 4 over here, and you'll end up with the same thing of the 17 square units. I think some other people probably have that on their paper, and I'll go back and I'll show that to you in a minute. But this answer doesn't make sense in terms of being height, but in terms of when you multiply them, it actually ends up giving you the same value on here. So apparently I'm jumping down to this one, this easy one down here, an isosceles right triangle, which I just threw it up there. Isosceles means sides are equal, means angles are equal, means it has a 45 and a 45 because it also is a right triangle. Hypotenuse is 10, so I threw that on there. So this kind of relates to this one up here. These are both the same. If you use ratios, your 1:1 to rad2 ratio, I think you can quickly get 5 rad2 for that side by dividing 10 by rad2. Or you can certainly use some sine and cosine and get a value on there. Whatever you get for these two, as a decimal or radical, you then multiply them, divide by 2, you should get 25 square units. So again, you can use sine or cosine, you can use the ratios. 5 rad2 times 5 rad2 is 25 times 2, but at the end you're divided by 2, so you get back to 25. Alright, last formula on here, so flip your page over. We're going to get into the trapezoid. Hopefully you look at that and go, yeah, trapezoid. So this little fill in the blank here is showing you that the area of a trapezoid is actually the sum of 2 triangles. So take that trapezoid that's on your paper and just draw another diagonal in, kind of like we did in the rhombus, but you're only going to draw one diagonal. I'm going to pause this for a moment here.